Have you ever noticed how a spoon inside a glass of water looks bent or broken? Or how swimming pools always seem shallower than they really are? That, my friends, is not magic, it's physics, specifically, refraction of light. When light travels from one transparent medium into another, say, from air into water, it doesn't continue in a perfectly straight path. Instead, it changes direction. And this bending happens because light travels at different speeds in different media. In air, the speed of light is roughly 3 times 10 to the power 8 meters per second. In water, it slows down to about 2.25 times 10 to the power 8 meters per second. And in glass, it's even slower, about 2 times 10 to the power 8 meters per second. If light travels slower in a medium, we say that medium is optically denser. If it travels faster, it's called optically rarer. Remember, optical density is not the same as mass density. For example, kerosene floats on water because it's physically less dense, but it is optically denser because light travels slower through it. When light hits the boundary between air and water, part of it reflects back and part of it bends into the water, and that bending is what we call refraction. Let's first look at what happens when light travels from a rarer medium, like air, into a denser medium, like glass. When this happens, the light slows down. And because of this change in speed, the light ray bends towards the normal, the imaginary line perpendicular to the surface at the point of incidence. In this situation, the angle of refraction R is smaller than the angle of incidence I. We can measure the bending using the deviation, which is given by delta equals I minus R. This slowing down and bending towards the normal is exactly why a coin at the bottom of a glass of water appears higher than it really is. In the diagram, you'll notice that the incident ray makes a bigger angle with the normal than the refracted ray does inside the glass, showing it greater than R. Now, let's reverse the situation. What if light is moving from a denser medium like glass into a rarer medium like air? This time, light speeds up as it enters the rarer medium. And because it's moving faster, the refracted ray bends away from the normal. Here, the angle of refraction R is greater than the angle of incidence I. The deviation in this case is calculated as delta equals R minus I. This is the reason why a straight stick placed in water appears bent at the surface. Your eyes are seeing the refracted path of light coming from the submerged part. As the diagram shows, the refracted ray in air tilts further away from the normal line compared to the incident ray inside the glass. But what if the light ray enters the surface at exactly 90 degrees, that is, perpendicular to it? When the angle of incidence I is 0 degrees, the light continues straight without bending. The angle of refraction is also 0 degrees and the deviation is 0. That's why in some optical instruments, like certain microscopes and endoscopes, engineers use normal incidence to prevent image distortion. In the diagram, you see the light ray passing straight through without any deviation. Now you might be wondering, why does light bend at all? The answer lies in the change in speed when light enters a medium of different optical density. Imagine pushing a trolley from a smooth floor onto thick carpet. One side slows down before the other, causing the trolley to turn. Light behaves similarly at the microscopic level. The greater the difference in optical densities between the two media, the greater the bending of light. Remember, refraction happens at the surface, exactly at the boundary between the two media. This is also why a swimming pool looks shallower than it really is. Your brain interprets the refracted light paths as if they were straight, giving a false perception of depth. Refraction doesn't just happen randomly, it follows to very precise rules known as Snell's laws. Law 1, the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. Law 2, The ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. Mathematically, sine of I divided by sine of R equals mu sub 1 2, where mu sub 1 2 is the refractive index of medium 2 with respect to medium 1. This refractive index is a measure of how much light slows down in the second medium compared to the first. As you see in the diagram, all three, the incident ray, refracted ray, and normal, lie perfectly in one plane. Let's solve a quick problem to see how Snell's law works in practice. A ray of light moves from air, where mu equals 1, into glass, where mu equals 1.5, with an angle of incidence I equal to 40 degrees. We need to find the angle of refraction. Step 1. Write Snell's law, sine I divided by sine R equals mu sub 1 2. Step 2. Substitute the values sine 40 degrees divided by sine R equals 1.5. Step 3. Rearrange to get sine R equals sine 40 degrees divided by 1.5, which is approximately 0.428. Step 4. Take the inverse sine R equals approximately 25.3 degrees. So, the refracted ray bends towards the normal, making an angle of about 25 degrees inside the glass. As the diagram shows, the incident ray in air is more tilted while the refracted ray in glass is closer to the normal. Now, let's see what happens when light hits a boundary straight on, that is, at normal incidence. In this case, the angle of incidence is 0 degrees. Since the light is going straight, it doesn't bend at all. Mathematically, the angle of refraction R is equal to 0 degrees. And the deviation, which measures how much the ray bends, is also 0 degrees. So we write it as R equals 0 degrees and delta equals 0 degrees. This explains why in some optical instruments, when light enters perpendicularly, there's no change in direction and no image distortion.